Hello all and welcome back to the filter design series. Today we'll be looking at distributed elements specifically for low pass design, and we'll be looking at one specific design, the stepped impedance filter. So why do we do distributed elements? At higher frequencies, around a few gigahertz and above, the values for lumped elements start to become impractical as they become too small to actually realize, and at the same time, the physical length of the circuit starts to approach a point where it can be electrically large and still inside the form factor that we'd like as the frequency gets high enough. Their implementation is also quite simple, as we are already doing traces on the board, and we can just use those to create the filters that we want instead of having to add elements on top of the board after the fact. A wide variety of options exist that can be tailored specifically to your design. For this video, we're only going to be looking at the stepped impedance design though. So the stepped impedance filter is perhaps the simplest of the distributed element filters, as it just alternates between high impedance, which are thin lines, and low impedance, which are thick elements, to create a low pass filter. Their electrical performance is not as great as some of the other options out there. However, they are quite simple to design, and if you have a case where you don't need high selectivity, they could be the right filter for you. The one caveat to this is also you can only use them to create low pass filters. So in this design, you can't modify it in any way to create a high pass or a band stop or a band pass. Assuming that we have a short length of the transmission line where beta L is much less than pi over 2, we have an equivalent circuit something like this. And you can already look at this and say, oh, well, that kind of starts to look like a low pass filter. And if we look at what the values for these impedances are, we can see that as we create a larger characteristic impedance of that line, this value starts to tend towards 0. This tends towards beta L, which is already small, so this B value approaches 0. And tan of beta L over 2, when beta L is small, approaches beta L. So we can approximate out to say that the impedance of this element here would be Z naught times beta L, and that's going to be a positive impedance when we have values less than pi over 2. So we can actually create an inductor out of that, and we can use the values we had in the last video and do some algebra to solve out for what beta L should be, that we plug those values in and get the inductor that we were using in the previous designs. Conversely, for the shunt element, if we want to make a shunt element, all we have to do is make the impedance of the line very small, and then we get that Y naught beta L approximates that shunt admittance, and we can then solve out for beta L, plug in the values from last week for that capacitor and the characteristic impedance of the system, and it will give us the length of the line that we need to substitute out for that shunt capacitor. So how do we determine what our high and low impedances should be? Well, if we looked at the equations and the assumptions we made, we should know that the higher for the high impedance and the lower for the low impedance is ideal. However, depending on what type of transmission line you're using and your manufacturing capabilities, you may or may not be able to hit certain values. You'll find for a microstrip, somewhere around 20 gigahertz on the low end for your lower impedance, 20 ohms on the low end for your impedance, and between 110 120 depending how thin you can make that line for your high impedance. So we're going to do a distributed filter design example using the same example we used last week, except instead of using the lumped elements, we're going to use the stepped impedance design. So we're going to create a low pass filter with a cutoff frequency at 1 gigahertz that has attenuation of 20 dB at 2 gigahertz. We go through the same process we went through last week, and we decided to design a Butterworth. So we grab the Butterworth table, and we say that it has to be a fourth order to meet those design requirements. Once we know it's a fourth order, we look at the table from the book, and we grab our G values. We have to pick the same design criteria as the lumped element, because we're replacing the capacitor and the inductor with transmission line. So I'm going to again choose a capacitor first, just to be consistent with the video last week. And now that we have these values, this is where we're doing something different. Remember last week, once we took these values, we had to renormalize them into actual discrete elements, but now we're going to convert them into transmission line lengths. So using the equations that we figured out earlier in the video, we're going to plug each one of these values into these equations, where the characteristic impedance is 50, and then the Z high and Z low are the actual impedance of the line that we're using. And I've written these down next to each one just so we remember. And once we plug those in, we get the radian length out. And I've gone ahead and converted those over into degrees. And we can see that none of these values are over 45 degrees. So you want to keep the lengths of these lines under 45 degrees, because that's an assumption that we made when creating these equations. You'll notice that beta L2 here is very close. And if I had picked any value less than 120 ohms, I probably would have gone over 45 degrees. So sometimes you'll come up with your design and you might be a little conservative in how thin you want to make that high impedance line, and say you pick 110 and find out that you have to go higher in impedance to make that work. And then you have to go back through and do that. So once you get these values, you can go ahead and plug them into something like line calc, where you give it the characteristics of your substrate you're using. You use the impedance to figure out how wide that line should be, and then you use the beta L to figure out how long that line should be. And when you plug those all together and feed them in with your characteristic, in this case 50 ohm lines on either end, you'll get a functional low-pass filter.